All right. So, that being said, here are some cases where there's some general terms, but there's a reason why these are structured the way they are. Find the curvature of a circle of radius A in R2. All right, so two-dimensional situation here. What I'm looking at, if I'm dealing with a circle, is something in the form of A cosine theta, comma A sine theta. All right, coefficients should be the same, all right, because they represent distance. All right, so following the process, and the reason why I can ask these questions rather than like in the last case is because these are very, very clean. All right, if I find r prime of t, I'm looking at, so just a derivative, we're looking at negative a sine theta, a cosine theta. The magnitude would be the sum of the squared values. So a squared sine squared plus a squared cosine squared, drop the negative. We have a GCF of a squared that can be rooted out of the whole thing, giving you an a times the square root of sine squared a plus cosine squared a. Oh, I forgot my theta. And sine squared plus cosine squared is equal to 1. So a times 1 is a. All right, so if I'm looking for the unit tangent vector, I'm looking at t of t is going to be equal to negative sine theta, comma cosine theta. All right, because all you're doing is taking your r prime of t and dividing it by its magnitude. All right, so that's nice. Really, when you think about it, I mean, the unit circle is defined as cosine comma sine. Okay, so with a coefficient of 1. So that's why it's unit. It's a unit circle. It's of a single unit. Radius is equal to 1. Right? So it makes sense that this would be the derivative of whatever the original function would be with a radius equal to 1. Right? That's the definition of a unit. So now we have to go through the more interesting part of it, which is to find the derivative. So t prime of t. All right, in general terms, but still not bad because we're working with basic trig function sines and cosines. So the derivative of negative sine is negative cosine. Derivative of cosine is negative sine. I need the magnitude of that. Drop the negatives when you square them, obviously. But cosine squared plus sine squared is the same as sine squared plus cosine squared, so it's going to be 1. Square root of 1 is equal to 1. All right, so the magnitude of the unit tangent vector is going to be equal to 1. Now, when I want my kappa, I'm going to take that 1 and put it over the magnitude of my derivative function, which we determined was a. All right, so kappa is going to be equal to 1 over a. All right. Now I'm just going to make a little note here where a, you don't have to write this, I'm just doing this just to kind of bring it all together, where a represents the radius of the circle, and so what we get from this is the idea that the curvature of any circle is always going to be 1 over its radius. Okay?
Why aren't all circles equally as curvy?
So, little circle, if you're traveling around just tracing it with a ruler, for example, you really got to kind of like bend that ruler as you go. But if you have a ginormous circle, you can leisurely move that ruler as you go around. So a large circle, a very, very large circle, like some segments of that could almost appear linear, right? And so what this gets at is the idea that if you have a circle with infinite radius, right? So just imagine that, like a circle that's increasing in size, becoming so substantial that, you know, like you're standing on, you know, a circle right now. You know, we create things that look linear all the time, but they are on the surface that has a curve to it. But the circle, or, you know, the path along the sphere is so large that everything appears linear. What you're ending up with is something that definitely is less curvy than something that would be much, much smaller, right? So that's the idea that, you know, like if you were to limit this, for example, and say the radius is approaching infinity, what would my kappa be approaching? 0, right? So if you could ever apply infinite radius, what you're creating is something that would become linear, right? If you could actually get to infinite radius, right? So you want to be thinking like small circle versus a galaxy, you know, like the circular boundaries of a galaxy. If you're looking at any sector of that, actually that would be a segment, but if you're looking at any portion of the circumference on the boundary of a galaxy, it would appear linear, right? Just based on the size of it. All right. So the next one, you know, same general idea, except you're dealing with something in 3 space. And it's got a little bit more, or a little bit of a different sort of feel to it. But then the curvature for any straight line in R3. So I'm going to put a star on number 11. Number 12 I'm actually going to get you set up on, because step 1 on this is probably the hardest thing. And then after that, I think it'll all kind of make sense from there. So we want any straight line in R3. So I need 3 components. Any of which could be a linear function. All right, so when we're dealing with a vector value function that is a line, any or all parts, any or all components of that vector value function could follow the model y equals mx plus b. All right, but we could have 3 distinct m's and 3 distinct b's. So we need to distinguish them from one another. All right, and also we're working in terms of t here, so we might say something like m sub 1 t plus b sub 1, m sub 2 t plus b sub 2, m sub 3 t plus b sub 3. The good news is, well, derivative is going to be pretty easy, because we know the derivative of a linear function is just its slope. So that gets you to m sub 1, m sub 2, m sub 3. And the magnitude, also pretty easy. I mean, to carry out the process, you're not going to be able to figure out anything numerically from this, but you can make the determination that the magnitude would have to be m sub 1 squared plus m sub 2 squared plus m sub 3 squared. The unit tangent vector, wow, that's not going to be pretty. but what results from it will be. Actually, let me go a little higher here. And I know I said I'd get you started on it, but I'm actually just doing the whole thing right now. In case anyone's wondering. So each component of R prime is going to be put over your magnitude.
Would it be wrong if you put the magnitude once and then the three ends with commas? Instead of writing everything together?
No, it wouldn't be wrong. That's fine. The next step is finding the derivative. So it depends. In this case, it's not going to matter one way or the other. But depending on the nature of this vector value function, you may need to end up in this format one way or the other. But in this case, it doesn't matter at all because t prime of t is equal to what? Nice round number. What do we say? Do you see any t's in there? So what is the derivative? 0. Oop, I put one too many. Exactamundo. All right, and so then what would be the magnitude? Magnitude would be equal to 0. And so therefore, what would kappa be equal to? 0. 0 because it had to be, because it's a straight line, but also because the kappa formula has t, the magnitude of t prime of t, as its numerator. So unless the r prime of t magnitude is also 0, which it's not, all right, unless you were dealing with something, some linear functions, a set of linear equations in which all three slopes were equal to 0, in which case it would not be a straight line. It would be the 0 vector. Well, actually, it wouldn't necessarily be a 0 vector, but it would just be a numerical vector. It wouldn't be a vector value function. It wouldn't be a line. That's one thing I can say. You're looking at something that's going to be 0 over some real number, in which case result is equal to 0. All right. So number 13 we skip. I always have that one in there because if I run into a class that I really dislike, then it becomes required knowledge, but that is not the case here. And so we don't do it. Yeah, that's just how it is. Curvature, like I talked about this significantly in the last class. The way that we kind of focus on it is like, if we're going to look for it in a general form, it's going to be a fairly basic type of vector value function. If you're going to look at it in particular form, the curvature at a point, now you're talking about like maybe a beefier function, with the idea being that the calculator is going to handle a differentiation for you. So that's the trade-off. That's 48 for those of you wondering. So just again, the process, it's pretty straightforward. I mean, the formula kind of dictates what the process is. You're taking the magnitude of the derivative of the unit tangent vector, which is a mouthful to begin with, and dividing it by the magnitude of the derivative of the vector value function to begin with. All right? So that implies that you have to find the derivative of your vector valued function, So I need an r prime of t. All right, I prefer the vector notation rather than the ij notation. You may prefer the ijk notation. I don't think it matters. So negative sine of t, comma, cosine of t, comma, 0. All right, and that's because of the understood coefficient for k, which would be 1. All right, derivative of constants equals 0. Magnitude I really wish if people are going to have dramatic conversations, they would do it out of earshot of my classroom. Words to live by.
I like that one. That's great. I'll use it myself.
Yeah.
No, use it.
Use it your side. Look at yourself in the mirror. So we have that. Now, this is kind of, I mean, it's good news, bad news, but it also, I mean, and I don't think there's anything bad news about this problem because the numbers are nice, the functions are nice. But when I'm looking for my tangent vector, my unit tangent vector, I would be dividing my r prime of t by 1. So I could have just repeated my r prime of t. And when I go to find the magnitude of that, oh, derivative first, sorry, and then the magnitude, it ends up being a really nice situation. So I'm negative cosine t, negative sine t, 0. But you can see it's made up of the same, essentially the same ingredients as the magnitude for your derivative vector. So when I go looking for my magnitude of t prime of t, I can expect the same outcome. All right, because all I'm going to be doing, without showing all the work, is I'm going to be squaring a cosine, squaring a sine. Negatives are going to drop. The 0 is irrelevant. I'm going to be taking the sum of sine squared and cosine squared, which is going to amount to a 1. All right, square root of 1 is equal to 1. All right, so if I'm looking for my k, one over 1 is 1. Now, should have known that kind of going in, although if you don't consider the nature of the function, I mean, the function, new word, curvature of the function. If you don't consider that, you know, the nature of it going in, then you don't necessarily pick up on these things. What this is, it's a vector valued function, yeah, I mean, just in essence, but it's circular with height, with a constant height. So this is a circular ring in space. So it's still a circle, just elevated off the xy plane by 1 unit. So when you think of it that way, it should have every characteristic of an ordinary circle in an xy plane, except it would have a z value associated with it. All right, so if that's the case, then its curvature would also be modeled by what we determined in number 10, which is 1 over the radius of the circle. Now, if you're looking at, I mean, cosine comma sine is the definition of the unit circle. All right, the coefficient is equal to 1, so it has a radius of 1. So if that's the case, 1 over 1 would give you a 1. This really is all just supporting work to get to this idea, just like this would be supporting work, but really what it comes down to is I just need the answer. All right, so it depends on the question. On a test, I do like to throw, you know about a proof, and just like the last review, I'll give you the list of things that a list of proof possibilities, a little bit less in this unit than in the last one, but you know, you'll know what you're up against. But I also like to throw a gimme in there. You know, I honestly, I thought the first part of the first question on the last test was the gimme. I mean, there were other little ones in there where it was like, oh, maybe you could, if you look at it the right way, you could figure it out. But the first question on the first, the one where you create the graph, like type it into your calculator, hit graph, make the graph that came on your calculator on the paper, and draw some arrows showing how it was graphed. You know, go to the table to get some points. You know, I thought that was the gimme, right? This could be the gimme. If I say find the curvature and I don't tell you how to do it, if you know this relationship, kappa equals 1. If I'm really nice, find what is the curvature for a straight line? 0. Right? Because it has no curve.
Would you have us graphing a 3D shape on a test?
Simple 3D shape. We're going to go over that in a couple minutes.
So probably like a cylinder.
Like what we did last time, the cylinder, basically. I mean, I can barely handle a cylinder. The planes, I mean, if you blur your vision and stand at the right angle and look at it kind of at an upward tilt, you can kind of see what I'm going for there. Yeah, I'm not big on asking students to draw those on a test because I look at that and be like, yeah, I mean, I guess. It doesn't look anything like it should, but maybe I'm just not looking at it the right way. So I'd have to give everybody credit, so I don't like doing that. I can't draw a sphere to save my life, like the way that you're supposed to.
So it should be like smaller circles going.
Yeah,
And
like it always ends up looking like
mess.
yeah, it's a disaster.
Like Manosphere.
Yeah, I mean, what it ought to look like is if you ever use one of those egg slicers, like you put the egg and then you slice it. If you were to hold the egg up afterwards with the horizontal slice, that's what the diagram should look like.
Yeah.
If I tried to reproduce that on paper for you, I mean, you'd be like, yeah, it's not an egg. It's just not. You know, like it's like stop doing what you're doing. And it gets even worse for other conic sections, ellipses, and stuff like that. So if I can't do it, I'm not going to ask you to do it. But a cylinder, I can handle it. I can do it, which means that you should be able to handle it and do it. All right. Also means it ain't going to be pretty, and I'm not grading it on aesthetics. All right. I'm grading it on whether or not it's technically correct. Points are generally in the right place. The shapes look like they're supposed to look. Good enough for me. All right. Oh, and this is the one I said that we wouldn't bother about. I put the solution to number 13 up on my website in case anybody is very interested in something like that, but it's not something I'm going to ask you to do. Not quite the quote, but close enough. So yeah, velocity, acceleration, force vectors, things like that, those come into play. Terminal point of a vector valued function represents the position of the object at time t. Then r prime of t represents the velocity vector. All right, so it's the same relationship. Is that if you're talking about r representing the position of an object, then r prime would represent the velocity, and r double prime would represent the acceleration. All right, so if we're looking at a vector valued function in 3 space, then its derivative is going to be what it was before. So there's nothing new here. Its magnitude, same magnitude formula, it's just now we're applying a little bit of context. All right.
For some reason, the page before this was my last page.
Oh, that sucks. Oh, this is a really good page to have. Is that the case for everyone?
No, right. I guess they're.
I guess you're not going to learn. Let's see what happens. Oh, this is actually the very last. Okay, so it must have got torn off at some point. Anyone else need?
Oh,
No.
Oh, you're just taking a walk. Okay, gotcha. Does anyone else need the last?
No.
Ah. Yeah, but I promise I didn't suspect anything like cheating or anything like that. So I hate when that happens because I go on a spiel of how devious I am, and then I immediately screw something up, and that was just a whiff. So anyway, arc length. So that's still a thing. These are all in context. It's the distance traveled along a curve. Right. So the thing is, when you're talking about curves in space, you know, a vector can get the job done in terms of telling you the location or giving you a sense of the location. But if you're talking about movement along a path, you need arc length, right? So an arc length function might be what you're looking for depending on the situation. So if you're talking, for example, about a road going up a mountain, you know, that might be something like a conical helix, you know, so in which case it starts off with a circular base and it decreases in radius as it goes up until it reaches a peak. Obviously not perfectly a cone in real life, but for math class, of course, you know. So you're talking about velocity along that curve, you would want to do it in terms of arc length. But if you're just talking about position along that curve, then maybe you can just go in terms of the vector, right? But generally speaking, it still has the same hierarchy, and all of this stuff is really addressing that. The idea is that you have an R prime that represents velocity and an R double prime that represents vector acceleration. An additional fact, brand new information, you've never seen it, but well, maybe not in a math class. Newton's second law states F equals ma, force equals mass times acceleration, right? So the A part being the important piece here, because now we have a technique by which we could figure out the acceleration of an object. If we multiply it by its mass, then we'll have the force related to that object, all right? Oh, it's weird. I don't know why I put that there. We just did that. All right, whatever. Conceptually, it's not bad. Oh, okay, well, recall. That's the equation of a circle. All right, so find the force acting on a 2-kilogram ball moving in a circular path of radius 3 meters with a period of rotation being 3.7 seconds. All right, so the new component here is the 3.7 seconds. As the period of rotation, because you could be talking about a path of an object, but we want to also talk about the type of movement along that path. All right, so do you complete one turn around a circle every second? Do you do it every 20 seconds? You know, that would indicate speed, right? So we do have to address the force part of it, but before we even get there, we need a function, right? So the radius part is not a problem, right? That's just a coefficient. But I do need to know what all the other stuff that make up the equation would be. So the period of a sine or cosine wave, because really if you think about the circle equation in vector value form, it's cosine comma sine, but typically we're working with cosine of theta. Now I have to account for a new period. Right? The period of a trig function, cosine or sine, the formula for that is what? 2 pi over b, whatever the frequency is. All right, so 2 pi divided by the frequency gives you the actual period. All right. Now what they're telling us here is that the period is 3.7 seconds. All right. If I'm gonna generalize my model, I need to pop in the 3.7 seconds for the period. Which would make the b value in my model 2 pi over 3.7. I'm not interested in changing that into some disgusting decimal. I'll just leave it like that. All right. So my r of t has an a value, because they said the radius is 3, has an a value of 3, cosine, this is the new piece of information, 2 pi over 3.7 t, comma, 3 times the sine of 2 pi over 3.7 t. All right, for all the previous problems, we were just assuming that the period was 2 pi. All right, so that would make the b value equal to 1. So that's why it was always, for our purposes, cosine of t, sine of t. But it could just as easily have been cosine of 10t, sine of 10t, and so on.
Oh, never mind. I was trying to figure out because I thought you put down like frequency. I was getting very confused. 'Cause I thought- But then, like.
Well, I did it. I just put in the
I
frequency.
thought you were doing the period and putting it in units of frequency. I was like, wait, where is this going?
Oh, okay, got you. All right. So, what I need now is a velocity vector, because this is a position vector. So r prime of t, oh, that's poor quality r. Now, it's a little bit of baby chain rule here. Cosine has a derivative of negative sine, right? So it's going to involve a negative sine of all this stuff times the 3 times the derivative of my inner function, which is just going to be the coefficient anyway. So what we're looking at here is a negative 6 pi over 3.7 times the sine of the 2 pi over 3.7 t. And then same ingredients, just with a cosine. 6 pi over 3.7 cosine of 2 pi over 3.7 t. So that would be my velocity vector. Now, I mean, it's surprising to look at this and say, well, actually, looking at it isn't the surprising part. Me saying that it would be very easy to figure out the magnitude of the velocity, that might be surprising, right? Because if your two components are sine and cosine, it doesn't matter what the frequency is, because sine squared of anything plus cosine squared of the same anything is always going to be equal to 1. Right? So there's really no math there. Right? You're going to have a constant multiple that you can pull out, and then that would be the end of it. Right? If you think about a circle, the magnitude of the circle is always going to be equal to the radius. Right? So once you identify what the radius is, you have your magnitude. So in this case, the magnitude is 3. Right? The radius is 3. If I were to square each part, factor out, when I square it, I'd have a 9, factor out the 9, I'd be left with a cosine squared plus sine squared, which would go to 1. The 9 would root to equal 3. Here I would have, okay, 6 pi over 3.7 squared, whatever that is, but then that would be multiplied by sine squared plus cosine squared, which equals 1. Again, it doesn't matter what the argument is. So the magnitude of this would just be 6 pi over 3.7, whatever that is in decimal form. So the work is very minimal once you kind of get a sense of the relationships. Now, finding the second derivative is, you know, I don't know if it's anything you're overly eager to do, but it's still very manageable. Sine has a derivative of cosine, right? So it's cosine of all this mess times the negative 6 pi over 3.7 times the coefficient on the inside. So we're talking, that's exactly what we're talking. Negative 12 pi squared over 3.7 squared cosine meh. And it's the same deal, just without the negative sign. Oh, actually, with the negative sign, right? Because cosine has a derivative of negative sine. So negative 12 pi squared over 3.7 squared sine 2 pi over 3.7 t. All right. So, again, this is the r prime of t is my velocity vector. and this is the acceleration vector. Now, if all I need is the magnitude of that, I could just pull out the 12 pi squared over 3.7 squared and call it a day. That's going to end up being your acceleration. Might as well write the whole word out. As we talked about. So last class I made a little snafu on page 50, so I have to correct it. It was only at the very end, but it was. It took me a little while to figure out why I screwed this up. It's because number 2 should have been number 1. These 2 questions should have been swapped. So if somebody wants that for typo bonus, just because I recognize that I made the mistake doesn't mean I took steps to actually fix it. So. And I'm tempted to go back and look at the videos from previous semesters. I guarantee you I made the same comment. Oh, I'm totally supposed to switch these two, and I just never do it. So that's why I kind of count on you all to claim your typo bonus, because if you don't go for those points, I never remember to fix it, and then 5 years from now I'm still going to be drawing these stupid arrows. So anyway. So we'll take a look at number 2, and then we'll come back and take a look at number 1. We did most of what we need to do. It's a little bit at the end that I muffed up here. All right. So number 2, find an expression for the centripetal acceleration of any object following a circular path of radius r at constant speed v. Relate this expression to angular speed w equals theta over t. I'm sure that's a fancy name for w, but it's a w to me. All right. So first thing,
It's omega.
That's an omega?
That is a lowercase omega.
That's a lowercase that?
Yeah.
That's ridiculous. It's a W.
Never mind.
Oh. All right, so, okay, omega apparently. I mean, it kind of makes sense. You're going with Greek letters here and stuff. Wait, omega's a Greek letter, right?
Yeah.
Oh, yeah, thank God. All right, I got something right. Technically correct about something. Let me actually bring this in a little bit. All right, so r is going to be equal to, we're saying radius r, so that's kind of an issue because I'm already using r for something else. So since I have to, based on the question, designate this as r, I'm gonna capitalize that. All right. So normally I do r of t, but it's not the case here. All right. So r cosine omega t, comma r sine omega t. Let me actually take a minute and show you where that comes from, because that's kind of an interesting relationship. So off on the side here, I'm just going to draw a circular sector. Poorly, of course. Why not? All right, this is S. We have a couple of R's because they're supposed to be equivalent radii, even though my picture just doesn't look that way, and a theta. All right. So we have a bunch of ratios that we can create out of this. But this represents a distance. We think of it as arc length, but it's a distance. All right. And so we'll get into the calculus aspects of it in a second, but we come up with, you can say theta equals S over R. The other variations, of course, are R equals S over theta, or S equals R theta. All right. So those are some possibilities. But we also have a relationship that relates velocity and time. All right. So we're getting to that issue here, and that comes from this idea. It's just flat out given to us in the problem. All right, so omega is equal to theta over t. All right, so we can come up with a relationship that allows us to look at this as an angular component or in an angular fashion by equating distance to time, and that would give us, well, this would be my distance. All right. Although, maybe I'm just making this harder. You know, I'm just going to go with the simple explanation and then worry about the arc length stuff later on, because I don't know that it's overly relevant right now. It's kind of a cool tie-in, but if you cross multiply this, you get theta equals omega t, and that's where I'm getting my substitution for this. I'll talk about the relationship with this later on, after I go through the differentiation process, because I don't know if it's going to quite make a lot of sense right now until I actually incorporate some d this, d that business. All right, so let's just work off of this, but at least you have an explanation of why on earth I'm able to call this omega t instead of theta, because cosine theta comma sine theta gives us a circle. We can replace it with an omega t based off of that relationship. All right, so let's take the derivative. R prime, bless you, negative R omega sine t, and then R.
Omega still be inside of the
Yeah.
sign.
Oh, I missed the omega. Thank you. All right, and so then we would be looking at R omega cosine omega t. All right, now we're looking for acceleration, so I gotta do that again. All right, so and at this point, you could actually come up with a measure for velocity. It's not really difficult. I might as well do it, even though it's not asking for that, just because it's worth a little mini discussion. If I look for the magnitude of R prime, I'd be getting the squared values added together and then rooted. All right. So I won't skip that step this time, but it'll allow me to skip it in the next step. It was negative RW sine W. I'm saying W. It's slowly morphing into W's anyway. I try to put the extra oomph and pizzazz at the end, but it's just not working. So we're looking at R squared W omega whatever. All right, and you have that constant multiple, jeez, making stuff up now. The common factors of R squared W squared, which can come out of the whole thing, so R W. And the reason why I like these kind of problems is it kind of hits home the idea that it's sine squared of anything plus cosine squared of the same anything that's going to equal 1. All right. So from this, we now know that the product of the radius and omega, which represents the angular speed, is going to be equal to velocity, right? Because again, this cancels out to just an RW. All right, so that's the magnitude of capital R prime, but in effect, that means velocity.
And you can do the same thing for acceleration.
And you do the same thing for acceleration. So if you want to, at this point, you can make a substitution where you have R multiplied by the actual omega, which is theta t. And so that's what I was getting at before, but I didn't think it would make sense to bring it up at that point, where I was talking about theta equals S over R, S equals R theta, you know, all these different relationships. But if I were to just take, if I make a substitution here, R multiplied by what omega really is, it's theta over t, you get a relationship of R theta over t, and R theta is the arc length. S equals R theta. So you get S over t. And that's why I was emphasizing before that S represents the distance, because, you know, when we're talking about velocity, we're talking about distance over time, right? And so R times theta is the consequence of theta equals S over R, you know, just whatever relationship you remembered, you know, that's your distance. So you have distance divided by time. It's just distance in a circular fashion. All right, so it's a cool little development. But again, talking about it over here, I didn't think it made much sense. That's why I kind of switched gears. But anyway, the acceleration is what we're after here. Let me just thin this out a little bit. So I got to differentiate again. So sine is going to become cosine, so negative R omega squared. Cosine omega t, comma, R, negative R omega squared, sine omega t. And again, by doing all that work over there, it kind of gives me a little bit of license to say, all right, I see how this one's going to play out, because it was just, when I went for the magnitude, yeah, we could square it all out, clean it up, but it's just going to be whatever the coefficients are of sine
R
and
omega
cosine.
squared.
Yeah, R omega squared. All right, and again,
R theta over theta.
say again?
Theta R times theta over t, since that's ultimately theta over t twice.
Right, but we could write it as R omega multiplied by another omega. All right, which, you know, doesn't seem overly useful until we consider that, where is it? R omega was this was the velocity, right? So we can actually just swap that out for a v if we want, right? But we'd also have to account for this guy. But we could also do a full-blown substitution and have some, you know, powers all over the place. Either way would work. So we're looking at velocity multiplied by theta over t. All right, and so we have to get something in terms of V's and R's. All right, so that's a little bit of a weird occurrence, but if we consider the fact that theta equals S over R, I'll write it, I gotta bring it in a little bit. All right, and then this, yeah, it's still a distance. You know, you don't want to lose sight of that. All right, velocity is equal to distance over time. All right, and so distance would be equal to velocity times time. All right, so this would be saying v multiplied by vt velocity times time over r all over the t that was already there. I'll bring it out a little bit now. All right, and again, that's only because we know that s is equal to or represents distance. And if you're thinking distance, speed equals distance over time, then you take the speed and multiply it by time, or velocity multiplied by time, and that's equal to the distance. And when we clean this up algebraically, we're getting v squared t over r over t. Make it a complex fraction to make it a little nicer, put it over a 1, cleans all the way down to v squared over r. I don't think I can get it all in the same frame. At least not right now. But, you know, that's that one little component there, which is why I kind of emphasized that in the beginning. All right.
Nice derivation question.
Yeah, yeah. Little lengthy, but definitely a nice one. Just to assuage people's night terrors, I would be more inclined to ask you this one, the velocity,
Instead of the acceleration.
than the acceleration, because the acceleration could be a little juicy.
If you gave us the acceleration formula, could we have sort of like stopped once we had derived v in terms of Lumbo and like just substituting?
Yeah, yeah. All right, so then back to number one, and this is just me being in a groove at that point. I guess not a good one. So we needed to figure out the force that was acting on this ball, but it was moving in a circular path, and so I just jumped straight for F equals ma because that's where my brain took me. But we did need to account for an acceleration that would be related to a circular movement, all right? So this is assuming a linear acceleration, which is not the case, right? So actually, as it turns out, because now that we discovered this rule, had it been number one, then we would know we don't even have to go into the acceleration part of this. Coming up with the acceleration vector is very useful information, but if we know that the acceleration can be figured out just by, so I get rid of all this, acceleration is equal to v squared over r, then I'm going to take the magnitude of my velocity, which would be 6 pi over 3.7. All right, and that's for the same reason that these were r omegas and r omega squares. It turns out that, you know, when you're dealing with sines and cosines, it's just whatever the coefficient is. All right? It's always going to simplify out to that. So that's going to be my velocity. So I'm going to square that and divide it by the radius, which we knew going in 3. So I'm going to take my 6 pi over 3.7, square it, and divide by 3. All right, and that's going to give me my acceleration, which we can then pop into the F equals ma. All right, so I'll just get this up here. Six pi squared. And then I'm gonna F equals ma that. Whatever that answer is, which I'll display it all in a second. 2 kilograms. All right, so It's 2 kilograms multiplied by that result, which is approximately 8.651. And that was meters per second squared. So then double this. I'm looking at something like 17.3-ish. And that was, like we said last time, kilogram times meters per second squared, but you know that as newtons. But if you don't know that as newtons, then you know it as kilograms times meters per second squared. So that's an important thing to keep in mind. The units are whatever the problem dictates the units to be. Oh, I don't think I want a video of that. I want a...
I thought it was cans, not newtons.
It was totally cans. Yeah, you're right. My bad. My inconsistencies are starting to catch up with me. Use photo, pop it in. So just kind of tuck it in there. And, you know, so barring any calculation error, which I suppose is also a possibility, this should be a more reasonable answer. And feelings and stuff, I don't know. But they gave us an acceleration vector with some initial conditions related to velocity and position. So this is just taking us right back to Calc 1, really. I'm sorry, beginning of Calc 2, end of Calc 1. So it all depends on how those courses really played out. So A of t can be thought of as 0, 0, negative 10. All right. They have it in the IJK notation. I, again, like the vector notation. So velocity is the antiderivative of acceleration with respect to time. So velocity, well, the antiderivative of 0 is some constant, call it C1. The other 0 would be some other constant, C2, I don't know if it's the same constant, it could be, and then negative 10t plus C3. All right, what we do is we match that up, essentially, with the vector that they give us. They're telling us that the condition has it so that when t is equal to 0, the resulting vector is equal to 1, 1, negative 1. All right, so all that's telling me to do, if I actually compute v of 0, well, therein lies a significant problem. Oh, there's no constant to plug in. Yeah, okay. There is no significant problem. It's just me being stupid again. So if I plug in a 0, nothing impacts the 2 first terms, but the last term must be equal to a negative 1. All right, so actually let me write it as C1, C2, instead of skipping steps. C1, C2 would remain the same, and then your third component to your vector, you plug in a 0, you're going to get C3. All right, so that's telling me that v of t, in reality, is equal to, we know C sub 1 is equal to 1, 1, 1, and then we have negative 10t minus 1. All right, so the constants are the easy part. They get replaced, although I almost screwed it up, so maybe they're not that easy. All right, so then next up is the idea that position, R of t, All right, so we have to anti-differentiate v of t. So we're looking at r of t as being, let me just slide it up, t plus, now since we've already solved for C1, C2, C3 in the previous context, we're free to use C1, C2, C3 again. If you get nervous, you can go to C4, C5, and C6, but at some point you run out of like patience with subscripts. So I just default back to C1, C2, and C3. All right. So negative 5t squared minus t plus C3. I mean, some people just don't write the subscripts at all and just know that they're all constants that are different from one another. That's fine with me. If you forget, I'm not going to be there keeping track of your constants. I'm going to keep track of whether or not you did the work correctly and your final answer makes sense. But if you miss some subscripts here and there, I don't really care. And I don't know too many people who do. Well, actually, I know maybe one or two people. So, anyway, r sub 0 is equal to 2i plus 3j. So that's telling me that r sub 0, 2, I got a little stray mark here. Oh, it's stuck. Yo.
Where'd you get the ones from?
Like,
Is that just chose them to be C1, C2, C3?
Oh, the subscripts? Yeah.
Okay.
Yeah, I just made that executive decision. 2, 3, 0. R sub 0 is 2, 3, 0. Based on the given, it said 2i plus 3j. Didn't indicate k, so that's telling us that it must be 0k. Right? I'm going to apply an r sub 0 to this. Time it out, skipping steps. I'm confusing everyone. So r sub 0, based off of this guy, would be c sub 1, c sub 2, and then also c sub 3. All right, which is really, I mean, the best thing that you could hope for, because all the t terms cancel out, and all you're left with are the c terms, which is fine, and definitely very manageable, although you can see that there's a fair amount of work associated with this, regardless of the fact that it's very simple in terms of the substitutions, but 2 plus t plus 2 is what I meant. So walking and chewing gum at the same time thing is getting me. So negative 5t squared minus t. Yeah, the issue that comes into play is, you know, what if it's not a polynomial function? I mean, that's been the case for Calc 1, Calc 2, and now Calc 3. It's like, yeah, it's not bad when it's reverse power rule. But what happens when I need to know the antiderivative of an inverse trig function? You're like, well, I don't know those antiderivatives. Well, that could be a problem. I'll just send it out real quick, because I don't see why even now you wouldn't benefit from it. Just because I don't collect people's index cards on a day of a test, just because I don't want to deal with that. But as you know, I walk around and I look at them and cut them up as needed, which is awkward, as you recall. Really awkward. Last semester it was more awkward because like repeat offenders. But I'm just going to send out a formula sheet. It'll seem like a snarky thing. It really isn't. It's just the formula sheet from an old Calc textbook that I had. So let me just shut up and do it, I guess. These are for AP review at the high school. Oh, this doesn't need to be recording anymore.